Hi, I'm Margot Seltzer. I'm honored to be here today, coming to you from Vancouver, British Columbia. The goal of my talk today is to convince you to take on exciting projects, projects that you think have potential, even if maybe some other people are telling you that they're kind of crazy. I want you to pick projects because they excite you and you can't imagine working on anything else, not because they're guaranteed to be successful or that it's what all the cool kids are doing. What do I mean by projects that maybe make other people think you're a little bit crazy? I'll begin by sharing some quotes from paper and/or proposal reviews that I've gotten. This paper is nutty, but it's also very well done. Reject. This is a thought-provoking paper, though I would say it is a very, very far-fetched one. Reject. The paper is intriguing and made my heart skip a beat as I started reading it. I want every paper I write to make my readers' hearts skip a beat as they start to read it. Unfortunately, that too was rejected. It is virtually impossible to simultaneously satisfy the requirements that the metadata be contained in the data and that the processing code be part of the provenance. Rejected. And my all-time favorite review, this idea is borderline crazy. Accepted. So sometimes, even if you take a wild and crazy idea and try to turn it into something real, you can actually get published in this community. Now, I am not the only one who feels that sometimes review committees are overly harsh. There's an entire website called strongreject.com run by Jin Yang. And to be honest, I didn't take this particular strong reject personally until recently, but the website is full with cute quips, some of which I am sure people have gotten on their reviews, although some of them are in fact perhaps a little far-fetched. But even in the presence of strong reject, I want to encourage you to undertake the kind of research and write the kind of papers that make people gasp, that generate excitement, and that sometimes even infuriate them. One of my most vivid recollections of an OSDI conference was one where Martin Renard gave the talk about failure oblivious computing because I'd never seen people leave a talk so angry. And I thought, I want to write papers that generate that kind of emotional reaction. The way I'm going to try to convince you of this is to tell a story in 3 parts. Part 1 will be a very biased, Margot-centric view of how our field has evolved. And I'm going to claim that the evolution of our field is one of the reasons why it's really hard and sometimes feels very lonely to take on these really bold and courageous projects. And then with that as background, I'm going to talk about 2 different projects that I've undertaken that put me in positions where I genuinely felt like I was the fringe lunatic. So let's begin that journey. From where did our field come? It came from one simple question. How do you build a mechanical computing device? The way to answer that question is the field of computer systems. It encompasses hardware, software, programming languages. But very quickly, that community splintered into subfields. First, it was just software and hardware. Then software split. Operating systems became its own community, databases became its own community, and programming languages was yet another community. On the hardware side, we actually saw quite an early split between what was considered high-performance computing and other forms of computing. Operating systems quickly split into networking, and then what happens when you put networking and operating systems together? You get distributed systems, but that became its own community. Now, about a millisecond after you introduce networking and distributed computing, you realize that security is a really important problem. And pretty soon that became its own community. For reasons that continue to remain baffling to me, the database and storage communities became different communities. For other reasons that are unclear to me, scientific computing became its own community. And then in perhaps what I consider the most baffling new community of all, network systems emerged as something fundamentally different from distributed computing. Now, it's not just the software side that has seen this splintering. This has also happened on the hardware side. So mobile systems are their own community. Embedded systems, or what we might now call IoT, are their own community, although actually people who do embedded systems will claim they're not IoT and vice versa. Architecture itself gets split into more of the perhaps electrical engineering side of VLSI and other forms of architecture. And so we find ourselves with this jigsaw puzzle of different areas. And sometimes we even encourage people that your goal must be to become the best person in a tiny box. And I want to push back against that. I think you should become the person who does really exciting research that touches many boxes. And today, because it's 2020, you can take any of these boxes, you can sprinkle them with machine learning pixie dust, and you have an entirely new set of tools. Now, I think that what's happened here is that we have painted ourselves into these tiny boxes that make it much harder to do truly innovative work. I think personally, the most exciting work happens when you draw techniques from different boxes and apply them to problems in yet different boxes. So what I want to encourage you to do is to think about computer systems really broadly. Think about these different boxes as simply representing different tools and techniques that we can bring to bear on problems. And then go tackle problems, pulling those tools and techniques from whatever area seems most appropriate. For my first research story, I want to walk you through about 20 years of research on data provenance, focusing mostly on the more systems-oriented aspects of it. So provenance comes from the art world, where it typically documents the chain of ownership of a priceless work of art. So if I were to tell you, I have a fabulous Picasso painting I would like to sell you, you might reasonably ask, oh really, how did you get that Picasso? And not only might you want to know how I got it, but you probably want to know how the person from whom I got it, etc. So provenance has meant the full chain of ownership from the moment Picasso painted it until it came to be in my possession. And if I have such a verified document telling you that whole chain, that increases the value of my work of art. So that's all well and good for the art world. What does that have to do with data? Well, in about 2001, Peter Buneman and his colleagues realized that you could take data that comes back from a query in a relational database and identify precisely why a value is in the return set and from where in the database that value came. Now, relational algebra gave us a formalism in which to very precisely define where data came from. But in computational science, we frequently don't have that kind of precise definition. But, about a millisecond after the database provenance paper came out, people realized this idea of tracking information and where it came from was instrumental in both documenting computational science and potentially enabling reproducibility of computational science. Great, so I started with art, now I'm talking about computational science. What does this have to do with systems? Well, the systems piece started in 2004 when I was chatting with Jim Waldo on the ground floor of Maxwell Dworkin, which is Harvard's computer science building. And we were talking about the challenge of really making science reproducible. And I had this eureka moment. And I said, wait a minute, we're systems people. We control the horizontal and the vertical. So if we were the ones who were capturing provenance, we ought to be able to capture everything and really document where items came from. So I got pretty excited about this and started building what we gave the name Provenance Aware Storage System because it had a cute acronym of PASS, even though what we were really doing was building operating system provenance. Now, about the same time, Jennifer Whittam at Stanford was building a database called Trio, which was taking this notion of database provenance and generalizing it and saying it's also another way that we can represent uncertainty in databases. So if we have two uncertain elements and we know what their uncertainty is because we know how they were generated, we can also say something about the uncertainty of data that is used when you take those two data items together. So we start to see provenance research moving off in workflow directions. It's going in interesting places in the database world, and then we're starting to take it into the systems world. Now in 2005, Now, in 2006, the community gathered for the first time at a workshop called the International Provenance and Annotation Workshop. And people brought in their latest work. But more importantly, there was a conversation about how we were going to build provenance systems and how they were going to interact. And there was a movement to start standardizing provenance. And I, in my shy, quiet, and retiring fashion, tried to make the argument that we didn't know enough about how provenance was going to be used to standardize it. So that led others, not me, to suggest that we have a series of community events where we try to learn something about how provenance can be used. And this sequence of activities became known as the Provenance Challenges. And so in 2006, the first Provenance Challenge was launched. So here's the workflow that this challenge was all about. This happens to be a workflow that represents a brain imaging study. And most of the participants in the challenge were collecting provenance at the level of a workflow. So when you had to produce provenance to describe your query results, they produced pictures that looked like this. Here was the picture we produced for one query in the Provenance Challenge. And if this isn't clear to you, perhaps you'd prefer the 106 kilobytes of text output that this query produced. So you have to envision, everyone else is getting up there and showing their 5-node graphs, and we're showing this graph, and we're trying to make the argument that this is actually important and valuable. And of course, we're getting all sorts of questions like, why do you want all that? Who cares what the operating system is doing? You can't possibly claim that all that data is useful. And perhaps one of the more interesting questions is, what's all this versioning thing? So one of the observations we made early on is that every time a process does anything, reads something, receives a message, it becomes a new version of that process because the provenance has actually changed. And there was no concept of this in any of the other systems. They viewed all data as essentially static, or if you did something, you produced a whole new object and was totally unrelated to the first object. So we introduced this notion of versioning that I think at this point has become pretty widely accepted. But I think the fundamental problem is that all the other systems had gone to great effort to provide real semantic meaning to the provenance. And we were kind of saying, we don't need that. So what happened next? Well, what happened next is that there was a second provenance challenge. And this was about interoperability. The way the game works is that you run the workflow, you generate provenance, then you bundle that provenance and you hand it off to another team. Meanwhile, you take some other team's provenance, and now you try to execute all the challenge queries on that provenance using your system. So this was a great deal of fun. You can imagine those poor people who tried to use our data. And what we took away from that experience is that there is no single right level at which to capture provenance. And in fact, provenance at all these different semantic levels is actually valuable. And in fact, the key thing is to be able to connect objects at one level to objects at another level. And so we built PASS version 2, which really embodied this notion of layering. So the next thing you know, all of a sudden systems people are saying, oh, this provenance stuff, it's pretty cool. So there was secure network provenance. Now at this point, PASS was 2 years old. And as fish and academic software, it didn't really last very well. So we ended up having to make changes throughout the entire operating system because there really wasn't any kind of clean API that would let us add provenance. So it was a nightmare to maintain, and I wasn't going to ask graduate students to spend 3 years essentially doing nothing else but continuing to revise PASS to incorporate newer versions of Linux. So then a group from UPenn built Hi-Fi, they too recognized this maintenance problem, so they defined a very nice clean API into which they could plug provenance collection. Unfortunately, that API was their own design and wasn't widely adopted. So it took quite a while, but in 2017, Pasquier and company at the University of Cambridge realized that the standardization around Linux security modules gave us exactly the right API at which you could capture provenance. And this was a game changer because since 2017, CamFlow has now adapted to dozens of new releases, both major and minor, of Linux. And so we finally have a maintainable, sustainable provenance capture system. So you'd think that this would create like all sorts of excitement and people would start using it. But instead, a funny thing happened. It turns out people don't care about provenance. My assessment is that it's kind of like security. People want it, but they don't want to pay for it. And also, the level at which you can collect provenance in a general purpose fashion is never exactly the right thing that people want to do something useful. So I came to think about provenance as kind of like insurance. You never really want it until it's too late. Now, you could have just given up and said, we're just giving them the wrong thing. Why wouldn't they use provenance? Well, I like to think of it, it's candy, not cod liver oil, right? Provenance is big and it's bloated and it has high overhead. And what you'd really like, instead of trying to force cod liver down their throats, what you'd really like to do is offer them candy, something they really want. So we scratched our heads and stepped back and said, well, let's think about this for a moment. If we trace the history of provenance, we started with database provenance. Then we went off and did whole system provenance while the rest of the world did workflow provenance. After our whole system provenance, we realized that sometimes you need application level provenance. And what we thought was application level provenance actually turned out to require a language interpreter or language runtime. And so we realized we'd actually invented language level provenance too. Well, once you have this infrastructure and this collection of different kinds of provenance, you can start to think about provenance applications. So given these different kinds of provenance collection, what kind of applications might I build? Well, on top of whole system provenance, you can build things like intrusion detection. Given your application provenance and language level provenance, we ended up building a system called Starflow, which was really a cloud-based orchestration platform for Python programs. We then had some R provenance tools, and we used that to build a containerization technology. So the idea was you're a data scientist, you want your research to be reproducible, go to our website, upload it, and voila, you get a container for it. We then looked at the no workflow Python provenance collection system, and we built a program comprehension tool. And then we took up all our R tools together and sort of created a toolkit that lets our data analysts debug their code, summarize their code, build tools on top of their code. So rather than trying to get people to just adopt provenance, we gave them applications. And so we gave them a reason to adopt provenance. And most recently, I've been talking to people in a wide range of disciplines, from archival science to mining to natural gas harvesting. And we're looking at supply chain provenance. So what started out as a like, hey, we could do something in the operating system has grown into this enormous ecosystem. What are the high level messages that I take away from that? So first of all, it's okay to be the fringe lunatic. And you don't need to know exactly where your work is going. Research should be serendipitous. You should see opportunities and seize them. But I think one of the more important lessons is that if no one is adopting your research, it's really worth asking why. And if you have to do things that we might consider marketing, it turns out that's really not a dirty word, right? Writing papers is a form of marketing that we accept, but there are other forms of marketing that we should think more about. For example, making your code usable by others, figuring out why people aren't adopting your work, talking about it in a language that someone other than computer scientists will understand, and helping people build upon it to do interesting things. You don't have to do all the work. So yes, we were the fringe lunatics. Was it worth it? Absolutely. Now you might be saying, but wait a minute. This started out as a storage project and you do storage. So even, how uncomfortable really was it to be a fringe lunatic? Well, I'll tell you, it was pretty uncomfortable. But what I'm going to do now is move into a different area where not only didn't I really have the background to do it, I didn't even realize exactly what area I was getting into. So you could call this bold, you could call this fringe lunatic, or you could just call this like not very smart. Let's call this project The Long Road to Program Synthesis. It all started in 1999 when Norman Ramsey came to Harvard and released C++, which was a retargetable assembly language. Then David Holland, my research staff assistant, came to me in 2004 and said, Norman's using machine descriptions to build things like compilers and debuggers. And we started brainstorming a little bit. We added Ada Lim to the discussion, and we came up with this really wild and crazy idea called an architecture a day keeps the hacker away. The idea is that we'd started to move to the cloud. We were in a complete x86 monoculture. So once a hacker figured out how to subvert a system, they could get into all systems. And we thought, well, what if you could take these synthesis tools that Norman was building, and we could synthesize not only things like compilers and debuggers, but we could synthesize a virtual machine and the operating system for the virtual machine. Then, if you wanted to run a cloud installation, you could simply generate an infinite number of virtual machines. Everyone would have a different architecture, and in theory, it would be harder to subvert the system. So this seemed like a great idea and a lot of fun, but who was gonna pay us to build a new operating system and synthesize virtual machines? And this was kind of wild and crazy. Fortunately, in 2015, DARPA launched the BRASS program, which was about software sustainability. So what were they really after? Well, the idea was that, they had an evolving ecosystem and they wanted mechanisms to infer the impact of such evolution on application behavior and performance and automatically trigger transformations that would beneficially exploit these changes and provide validation that these transformations are correct. Or extract whole system specifications. Or leverage new programming abstractions, program analyses, and compilation methodologies to correlate application behavior with salient ecosystem changes. And this one's a little close to us, exploit new runtime systems and virtual machine implementations structured to facilitate the efficient integration of these transformations. So we didn't really fit in any of these buckets. But I made the argument that if you really truly want sustainable software, you have to be able to adapt to new hardware. Because in reality, a lot of these embedded systems like unmanned underwater vehicles run really, really, really old hardware and operating systems. I won't tell you exactly how old, but just think really old. Because they get a new processor, they can't upgrade the software fast enough. So my argument was the stuff we're claiming we want to do is crucial to being able to adopt new hardware. And fortunately, we were lucky to be adopted by Charles River Analytics as a subcontractor in this BRASS program. But who was really in this program? Well, there were machine learning people, and there were other AI people who do things like probabilistic reasoning and multi-agent systems and planning. And there were lots of programming languages people and roboticists and verification folks. And then there was us. So once again, there we were out on the fringe. So to put this in context, BRASS is this big DARPA program. Princess is one of the performers, and it actually is an acronym, and I can never quite remember what it means, but it's a great name. And then Harvard is this, subcontractor inside the Princess project. And here was the story that we told that we wanted to do, and we were 100% sincere. So imagine you have an unmanned underwater vehicle or a cute little submarine, and you get a present in the mail, and it's a new computer. And along with that computer, you get a pile of specifications. Now, historically, what you would do is you would then sit down and start writing a port. But instead, in our world, what you do is you write a machine description file that describes that hardware. So you spend some time poring over the specs and translating those specs into a formal description, or in a perfect world, the vendors actually give you those formal descriptions. Then what we do is we take those descriptions, we combine them with sort of templates for things like assemblers and linkers. We put that through a synthesizer, and now we have a new tool chain for our new hardware. So that's step one. Well, we're going to do that same approach for building an operating system. The way we're going to describe our operating system is we'll have the standard stuff in the machine independent layer. And then you'll have sort of a hybrid operating system where for the machine dependent code, instead of actual implementations, what you'll have are specifications. And the idea is that you then take those machine description files and those specifications, and you produce the source code for the operating system. Conveniently, you have an assembler and linker. So now you take that OS code, you feed it to the assembler and linker, and suddenly you've got a new operating system. And our goal was that the operating system was going to run all the other software that our collaborators on the project were going to build, which meant we were going to run an entire Java virtual machine. I'll give you a sneak preview. We didn't really get that far. Anyway, once you build this new operating system and get all the application software, you download that onto the computer, and then finally you put the new processor in your submarine and you're off and running. And so rather than having to take a sub offline for a long time, the idea was the sub comes into port and you can basically have everything synthesized, within days after the new hardware platform comes out. So it turns out that this is really all programming languages work. Who knew, right? Machine description files, that's a language design problem. This OS source code, that's sort of a language design problem. Turns out synthesis, that's a language problem, or programming languages problem. So what were we doing programming languages? Well, there's a little bit of OS work. I mean, we did have to build this operating system. So this is where we ended up. And the way I think about it now is that if you take sort of an article about full stack development today, you get a word cloud that looks like this. And I'm going to hypothesize that if you think about what a full stack developer tomorrow looks like, it's going to look like this. And this is the word cloud that you get when you start to take some of the things we've written and generate a word cloud. And a side effect of building software this way is that the software is verified by design, right? In order for synthesis to succeed and for you to get an implementation, you've also verified it. That's kind of attractive. So I think that this was actually a good vision. I still think it's a good vision. I'll tell you where we are in a minute, but how far did we get? I told you we didn't run a Java virtual machine. So we got 2 different operating systems that we took parts from. We ran on 4 different processors, and we extracted 17 different use cases from these operating systems, which were little tiny snippets of code that we could synthesize. And when I mean little, I mean little. And we're going to come back to that in a minute. And the good news is that we were able to synthesize most of those. And we're still currently trying to take all those pieces, put them together, and actually run an OS. And I am optimistic that by the end of this year, we will have done that. So what do I think about when I think about this project? Was it an unqualified success? No. Was it a research success? Absolutely. We learned a ton. We did things people hadn't done before. Did we learn a ton? Absolutely. And more importantly, has it informed future work? Absolutely. Should we have done it? Yeah, heck yeah. Were we crazy? Absolutely. Now, what are the takeaways from this? Well, they fall in 2 categories. Some are motherhood and apple pie, and we should have known them at the beginning, and we probably did, but it's always good to be reminded. So one miracle per project. We had lots and lots of miracles. The tool chain was a miracle. The specification languages were miracles. The synthesis was a miracle. Putting it together was a miracle. We had a lot of miracles to go around. Experiment early and often. We spent the first year coming up with use cases, learning the OS, playing with synthesis, but we didn't start doing end-to-end testing that first year, and I think that was a mistake. So you really need to start running tests and experiments and little things early, even if you're still in the process of learning. One thing we learned, now I'm moving into the things that are more project specific. So we always said we wanted to synthesize the machine dependent portions of the system. And what we failed to realize is that there are machine dependent portions and then there are machine specific portions. So the boot sequence is really not just machine dependent, it's very machine specific. So that remains an open problem that we really didn't think about in the context of Princess that we're starting to think about now. And so this is work that has now moved with me to UBC. There's also a question about how much effort does it take to write a specification and how much value do you reap from that specification? So if it takes a lot of work to write a spec, but I can use it in a lot of places on a lot of different machines, it might be worthwhile. In a perfect world, writing the spec's really easy, and then you reap a lot of value from it. Another thing that I've really embraced is this idea that synthesis is really a spectrum, and it ranges from input-output examples to a compilation to counterexample guided synthesis, and sort of lots of places in between, including things like templating, which was the vision I really had in my head. When we talk about real synthesis, though, SMT solvers are great, and they've come a long way, and they are amazing. At the same time, constructing the right problem to give to the solver is hugely important. And so your synthesis engine really has to be pretty savvy about what the SMT solver is going to do. And then finally, it turns out assembly language is really hard to synthesize for a variety of reasons. So where are we going to go next? Well, when I step back, one of the things we did is we decided to try to do this in the context of an existing operating system. And operating systems are designed for human portability, not synthesis. So you actually will do better if you build a system specifically for synthesis. So that's what I wanted to do, but I wanted to broaden that definition of OS to really be any kind of system software. Because recall that I said you need to synthesize really tiny pieces. So if we're going to synthesize really tiny pieces, why don't we synthesize for really tiny platforms? So I've been thinking more about things like hardware accelerators or IoT devices and special purpose hardware, where the system software is not the point of the hardware, but there's a bunch of things that they all kind of need to do, like move data around and do communications and stuff. So could we build little modules that would work on a variety of platforms? So the answer is that's what we're going to try to prove. So what are we doing is we're first specifying what I call teeny tiny operating system components. So much smaller than anything you would normally think of as a module or even a file in a system, right? So just the synchronization operations or a context switch of just the hardware state. And then you can start to make that bigger. So teeny tiny little pieces that we can specify in a machine independent fashion. So again, specifications. Tons of research questions. What are these primitives? What do they look like? How do you specify them? And how do you do that in a machine independent manner? So what is a component in this world? Well, it's a chunk of functionality. And because we're talking about OS code, it better have a security specification. Right? These need to be rock solid. Then it has to have an API specification that says, what do you expect at the interface? And in order to support things like monitoring and auditing, I also want an introspection API that lets me ask questions about this component. Well, we have lots of research questions there too. So how do you enforce the security specification in the presence of an introspection API? And so we've got some really deep programming languages research going on to really try to answer that question. So I'm not involved in that. I just sit on from the sidelines and cheer, because where I want to go is I want to take these specifications of operating system components, machine descriptions, similar to what we did before, the machine dependent part. We need to decide if we need to specify those differently, so more research questions. But what I really want to do is take those things together, do synthesis, create a library of these components such that you can put them together to build system software for lots of little devices. So specifications at the low level, implementation at the higher level, and the question is, can we actually do all this? The pilot projects that we're working on now, we are writing a teeny tiny operating system of components to work on IoT devices. And we're using the Unity specification language, not the graphics library, to generate code both for native Arduino as well as Verilog. And so the idea is that using these high-level specifications, we can build a cool little distributed system of Arduinos that implement interesting algorithms. So long road from, hey, Norman's got this cool C++ thing, to this new project called Velocity, where we're trying to build system software for tiny devices. But it's been a great ride. I've learned a ton of things I didn't know before. I got to be the Fringe lunatic again. And so I'd like to wrap up with the words of Ms. Frizzle, for those of you who grew up with Magic School Bus. Take chances, make mistakes, get messy, get your hands really dirty. I'd like to thank all the wonderful people who put great pictures on the internet that I can use. And on that note, I will give special thanks to all of my collaborators, and extra special thanks to Charles River for letting us realize one of our fantasy projects, funding agencies who let us do that, and also all of you who were critics or naysayers and harsh reviewers. Every one of those experiences made our work better. Thank you.